So this is chapter 13, problem 36, which says a sealed test tube traps 25.0 cubic centimeters of air at a pressure of 1.00 atmospheres and temperature of 18 degrees Celsius, and it will pop off the test tube if a net upward force of 10 newtons is applied to it. So we're asked to figure out to what temperature do we have to heat this trapped air in order to pop the top off the stopper. And we're supposed to assume that the air surrounding the test tube is always at a constant pressure of 1.00 atmospheres. So I feel like this is the original picture with the initial pressure and temperature, which I've gone ahead and converted Celsius to Kelvin, and we'll see why we need that in a moment. The volume and the diameter of the stopper. Later on, we want this thing to be heated up such that the situation is looking the same. The diameter is still the same. There's still air inside. The volume is the same. The pressure will be something different, and the temperature will be something different. But what we want to be the case is that at this point, although over here, since the pressure on the inside and outside is equal, you can imagine the forces acting on the stopper. There's a force going up from the pressure inside. There's a force going down from the pressure on the outside. But the net force is 0. Here, we want there to be a bigger force going up than there is going down, and we want the net force to be equal to 10 newtons. Okay, and we want to figure out what kind of temperature we need in order to make that happen. Okay, so conceptually, what kind of things are we dealing with? Concepts. Well, apparently we're dealing with pressure and temperature, so we can go ahead and write that down. Pressure, temperature. We're also dealing with forces, so the connection between pressure and force will be needed. So we'll write that down. Forces. We've also got air inside of a container that's got a fixed volume. We're relating volume, pressure, temperature. We might want to think about what kind of laws tell us how those quantities relate for gases. And air is, to a good approximation, an ideal gas. So let's go ahead and think about gas laws, specifically ideal gases. Okay. So, what kinds of equations might we need? And we'll add to this list if we need to: pressure, temperature, forces. The relationship between pressure and forces, since we're going to want to compute forces acting on an object that has a particular size, determined by a diameter, and there's different pressures, we might want to remember that pressure is ultimately related to force over area, or if you like, pressure times area gives you force. We're going to need that, I'm pretty sure. The other thing we've got to do is ask, how does pressure, temperature, volume relate? Well, if we're going to use the ideal gas law, then let's remember that PV is equal to the number of moles times the gas constant R times the temperature. Or we can write this as N, the total number of particles, times Boltzmann's constant Kb times T. Each of these are equivalent, but the main point is the product of pressure times volume is proportional to temperature. So let's see what we can do. First of all, let's see what the free body diagram looks like. We basically have it going on here. The free body diagram acting on the cork, or the stopper. It's got some mass. We don't know what it is, and fortunately we don't need to know. We've got an upward force and a downward force, and what I'm interested in what is happening afterwards. So this is after it's been heated. After heating. We know that the upward force is given by whatever the pressure is on the inside times the cross-sectional area of the stopper. So that going up should be P2 times the area of the stopper. That's the upward going force, right, from all the molecules crashing into the bottom of the stopper. Going down, you've got an atmospheric pressure, which is also pushing down on the stopper. So that's P on the outside. If you like, it's the same as P1. It's the atmospheric pressure. Or if you like, let's just write it as this, P1 times the atmospheric pressure. And I've probably drawn this in a slightly misleading way. What really matters here is the same area on the bottom and the top. So maybe let's just make this be a uniform stopper so you don't get confused about which areas we're supposed to be using. Okay. Anyway, given the fact that we're interested in a situation where the net force is equal to 10, we want to consider the net force, in other words, P2A minus P1A, we want that to be, well, that's the net force, and we want that to be equal to 10 newtons. All right. P1, and I'm leaving this all in algebra because I think it'll make it simpler and we can plug in numbers later. P1 is given. The area we can compute once we know the diameter. We can get the radius and do pi r squared. We'll do that in a moment. What we're interested in then is maybe seeing if we can figure out what is P2. Okay, ultimately, that's not what we want. The goal is to get T2, but if we're able to find P2, the pressure, afterwards, then we can probably figure out what the temperature is. So I'm going to go ahead and rearrange this equation so that I can solve for P2. It's one way to approach it. You can approach it in a different way if you like. P2 times A is apparently equal to, and again I'm going to get rid of the 10, I'm just going to leave it as F net. Net force plus P1A. And ultimately I can get P2 now. P2 is apparently equal to F net divided by A plus P1. Okay? And again, F net is known, that's 10 newtons. Area can be computed, and P1 is 1 atmosphere. So that's an equation that tells us what P2 is. We want to get the temperature. Well, the only equation I see over here in order to get the temperature might be this one that relates pressure, volume, and N and R and T. What I see here is concerning to me, though, because apparently it seems like you need to know either the number of moles or likewise the number of particles in the container in order to use this equation to solve for the temperature. That can seem problematic. The good news is that you have to keep in mind that apparently the product of pressure times volume is proportional to temperature. What that means is that pressure times volume divided by temperature is equal to NR, the number of moles, times R. And so if your container is fixed, then N is fixed. So I'm going to write this as fixed. Okay, fixed because the container is fixed. No particles are leaking out or coming in. R is a constant, so it's fixed. So this is, in fact, a constant. So what that means is the initial pressure, P1, times the initial volume, which is just V, divided by the initial temperature, is equal to the final pressure times the final volume over the final temperature. Okay, that's constant in time. Notice that the V actually doesn't matter. It appears in the same way on both sides. And finally, what I'd like to do is solve for T2. So maybe one way to do that is to flip both sides of this equation. So T1 over P1 is apparently T2 over P2. And therefore I can solve for T2. Okay. Apparently T1 times P2 over P1 is equal to T2. Okay. So basically we got this from the first part of the analysis, and from the second part of the analysis we see how we can relate the initial temperature to the final temperature. Okay. So let's go ahead and plug in our result from before into this equation and see what we have. Apparently we have T1 over P1 times P2. That's all of this. F net over A plus P1. And all that should be equal to T2. The reason why I'm writing it this way is ultimately I want to show you what happens when you throw all this in here. Apparently, this first term looks a little bit funky. T1 times F net over A over P1 plus the P1's cancel. This is T1. And this is, I think, a nice place to stop, and you can ask yourself, does this make any kind of sense? Well, what this tells you is the final temperature, it's equal to the initial temperature plus some amount, so it should definitely be bigger than it was before. By how much should it be bigger? Well, it's this higher temperature that you need is going to be higher the bigger the needed F net is, the bigger the net force is. And so at least this makes some kind of sense. It's consistent. It's not going to give you a lower temperature. So finally what we can do then is plug in all the quantities that we have. The initial temperature, which is 291.15 Kelvin. The initial pressure, which is 1 atmosphere, and should go ahead and convert that into pascals. So 1 atmosphere, recall, is 1.01 about times 10 to the 5 pascals. F net, that's 10 newtons. The area, this is probably the place where it's most easy to make a mistake. You have to remember that you've got this cork or stopper, which presumably has a circular base. You're given a diameter. We want the radius. So let me put this over here. The area is given by pi r squared. The radius, of course, is 0.75 centimeters, which is 7.5 millimeters. So you may want to write this like this. In units of meters, 7.5 millimeters is 0.0075 meters. And then don't forget to square it. So that's the number I'm going to stick in there. Okay. And then finally, plus the initial temperature of 291.15 Kelvin. That should give us our final temperature, which I've run out of room, so I'm going to just put it over here to show you that according to my calculations, this is the final result, you should find that T2 in Kelvin is 454.3 Kelvin. And when you convert that to Celsius by subtracting 273.15, that comes out to be about 181 degrees Celsius. As a reminder, we needed to convert from Celsius to Kelvin at the initial stages of the calculation because using the ideal gas law only works if you're using absolute temperature or temperature in units of Kelvin. Otherwise, this equation wouldn't make any sense because units of Fahrenheit or units of Celsius can go negative, and there's no way you can get pressure times volume to be negative. The temperature has to be greater than or equal to 0, and that's why we use the absolute or Kelvin scale. So here is your final answer.